Hi, this is Dr. Rimenacker. In this particular video, we are going to start exploring a very important idea, the idea of optimization. Optimization talks about making something optimum, making it the best that it can be. In some cases, best means a maximum. For example, in a business setting, you would like to optimize profit, make it the best it can be, as large as it can be. If you're in a business and you're talking about something like cost, the objective there is to minimize the cost, making it as small as possible while continuing to reasonably operate the business and serve your clients. We're going to look at ways to compute absolute maximum and minimum values on intervals. It's important to be on an interval because realistically, in the real world, we don't have an infinite amount of anything. So for example, if your question is, well, gosh, how many calculators do we make and sell? If you could make and sell an infinite number of them, that would provide an infinite profit. The problem is there aren't an infinite number of sales possible. Neither are there an infinite amount of resources available to create this infinite number of calculators. So what we're going to do here is we're going to look at ways to deal with maximizing or minimizing when you have restrictions. To take a look at or to understand how we're going to go about this process of locating absolute maximums and absolute minimums, where absolute literally means it is the best that it can be, we need to give a couple definitions here first. Understanding what absolute max and min means for one thing. Okay, suppose you're given a function f with some domain I. The domain, in many cases, when we're talking about production, will be a minimum number of units that you can make up to some maximum number that's possible. In this case, I'm just saying 50,000 calculators a week as an example. Okay. And that domain is going to list your restrictions, your minimum, your maximum. And the objective is to then find the absolute largest or best, in some cases minimum, value possible. A maximum, okay, is a value C. It's some X value in the interval. Remember, we just listed an interval. So if our interval is this 0 to 50,000, C would be a value somewhere between 0 and 50,000, including 0 and 50,000 as values. This f of C is a minimum if that value is less than or equal to any other y value on this interval. So for example, let's say our y values range from 42,000 up to 117,000. I'm just making something up here. The absolute minimum would be the 42,000. An x value that gives you that absolute minimum, okay, is the point you're looking for. If we're searching for a maximum, the second of the two parts in this definition, that means that the value that we come up with for y is going to be bigger than any other y value possible or equal to the absolute biggest y value possible. In the interval for y values shown on the right, the absolute biggest that f of c can be is 117,000. The x value that achieves that level is the x value we're looking for. Let's take a look at a theorem. Theorems are important rules for the game. Very important theorem with regard to this whole idea of optimization is that a continuous function on a closed interval. Now let's stop. Let's not roar past these two things. First, the function is continuous. That means it doesn't have any breaks. You can draw it by putting your pen or your pencil down and never lifting it, and you get the whole function. So the function has to be continuous, and it's on a closed interval. A closed interval is different from an open interval in that an open interval does not include the endpoints. A closed interval does include the endpoints. Well, what's the difference? If you have an open interval, this function does not achieve a minimum because if you pick this point here, somebody else will pick this point. Well, gosh, now I'm going to pick this one. And if you get out of magnifying glass, you can keep getting closer and closer and closer and closer to the x value that is the minimum, but never actually achieve it. It's a limit situation. Once you have a closed interval like that, now there is a lowest point that you can go to. And that lowest point is that solid dot right there. So we have a continuous function on a closed interval. If you have a continuous function on a closed interval, and remember a closed interval is going to have square brackets, not parentheses, okay, you will have a maximum somewhere on that interval, and you will have an absolute minimum somewhere on that interval. I've drawn a continuous function here. We have a variety of locations. This is a minimum. Compared to things around it, it is a low point. However, it is not the lowest point. The lowest point is there. This is what is referred to as a relative minimum. That means compared to everything around it, it's lower than everything that's close by. Similarly, this is clearly a maximum compared to things around it. Looking over the entire interval from A to V, it's not the highest maximum, so it is a relative maximum. This value down here at x3 is as low as the graph goes anywhere on this interval from A to B. X3 is the absolute minimum. We have next to it at x4 another maximum point. Notice this is a corner. It doesn't have to be smooth to be a maximum or a minimum. It is not the absolute highest point, but compared to things around it, it is a high point. So once again, you have a relative maximum. When we look at the next location right there, compared to other points around it, x5 is a minimum. It's not as low as you can get. x3 is as low as you can get. So it is referred to as a relative minimum. Now, B right here is clearly a maximum. And if you compare it to any other point from A to B, this is as high as the graph goes. This is the absolute maximum. Be mindful that an absolute maximum or absolute minimum can occur at an endpoint. In this case, the absolute maximum occurs at an endpoint, or an absolute maximum or absolute minimum can occur at a location within the interval. X3 in this example is the absolute minimum. Let's take a look at a couple of examples here. You're asked to locate the absolute max and min points on the interval for the function g of x equals x cubed minus 3x plus 2. Very important to notice here, first off, we have a polynomial. This is a continuous function. And we have a closed interval. We have a continuous function on a closed interval, so this theorem that is now at the top of the screen will apply. The theorem says we will have an absolute maximum point, we will have an absolute minimum point. It is possible to have two locations on a graph that are at the same maximum height, or two locations on a graph, or more than two, that are at the same minimum height. So you can have more than one absolute max or absolute min. But with a continuous function on a closed interval, you will have at least one. Okay, so how do we go about solving this? First thing I want to do is I want to locate my critical values. To locate my critical values, that means I'm going to take my derivative, set it equal to 0. So that says we're going to have this 3x squared minus 3 equals 0, or we're going to have 3x squared equals 3, x squared equals 1, x is equal to plus or minus 1. Okay, these are potential critical points. What I am interested in is focusing on the x value and the associated y value. So this actually works out to be a fairly simple section because we don't need to wade into first and second derivatives and things like that. What I'm going to do is between listing my critical values of -1 and 1, I'm also going to list the endpoints. One of the endpoints is -2. The other endpoint is 1. Then what I'm going to do is I'm going to enter in my function, the y value, x cubed minus 3x plus 2, into the calculator and go to the table. Now in this case, I'm just using the calculator I have in hand. Okay, so I've got my x cubed minus 3x plus 2 in the calculator. I'm going to substitute in -2, -1, and 1. I get values 0, 4, and 0. So we have 3 points. We have the point -2, 0. We have the point -1, 4. And we have the point 1, 0. Because we've taken a derivative and set it equal to 0, we know that we have accounted for all of the possibilities of high and low points. Okay, remember the first derivative will locate for you all situations where the function has a slope of 0. That'll be your max and min points. Given these 3 points here, or these 3 locations, the question is, which is the highest? Which is the maximum? Well, that means the biggest y value. This is going to be our absolute max. Now, where is the low point? Well, it could be at this end here, which would be an absolute minimum. Or it could be at this point here, which is also an endpoint and an absolute minimum as well. If you'll recall earlier I said you can have more than one absolute max or absolute min. Here we have one absolute max and 2 absolute mins. It's sometimes handy if you have more than one absolute max or min. It gives you choices. Okay? If we're trying to get an absolute minimum, we have 2 ways to do that. We can do whatever x equals -2 means, or do whatever x equals 1 means. So we have options. If we take a look at something like the second situation, okay, I now have the same function as I did before. My critical values are going to be the same values. They're going to be x equals plus or minus 1, okay, just like we had on the problem previous. And all we need to do now is evaluate our y values at the appropriate x values. Notice now our interval has changed from -3 to +1. Before it was -2. Our critical values are at -1 and +1. Okay, well, I have 2 of the values already. If I plug 1 into my function, I get 0. If I plug -1 in my function, I get 4. If I plug, what do we have here, -3 into the function, we get -16. This now gives us 3 points from which to choose a minimum and a maximum. We have this point, we have the -1, 4, and we have the point 1, 0. Our maximum, our absolute max, is right here. That's where the y value, 4, is the absolute biggest. Now, I'm going to compare this -3, -16, and the 1, 0. The one that is lowest now is going to be the -3, -16. This is an absolute minimum. The 1, 0 would be a relative minimum. Compared to things around it, it's lower than other points, but it isn't as low as you can go on that function for that interval from -3 to +1. Let's take a look at a couple of problems here. Let's say we're going to consider the same function. Aha, x cubed minus 3x plus 2. So we're going to continue working with this same function. I know first off that my critical values are going to be at x equals -1 or +1. So to get my absolute max and min, I need to evaluate my x values. -∞, -1, 1, and infinity. Okay, well, gosh, to do the first one here, this is going to be the limit as x approaches -infinity for g of x. We need to take a look at this. Remember, we're putting in larger and larger negative numbers. And if you cube a negative number, you're going to get back a negative number. So what's going to happen here is by cubing larger and larger negative numbers, the result that we will get back is a very negative value, -infinity. We've already done the -1. Notice up at the top, it returned a value of 4. 1 returned a value of 0. Now what we need to do is to consider the limit here as x approaches infinity of g of x. In this case, we're going to cube infinity and then subtract 3 times infinity. Well, infinity cubed is going to be enormous. Minus something else is just not going to keep up with it. Okay, so in this case, we have 4 choices for our absolute max and our absolute min. Okay, notice here, this is our min. However, can we actually get there? The answer is no. So this point, this next one will be a relative max. This point will be a relative min. Because we cannot actually get to either this -infinity situation here or the +infinity situation here, this particular function on this interval from -infinity to infinity has no absolute max and no absolute minimum. Well, that may not have ended the way you expected it to. It is completely legit to say there is no absolute max. It is also completely legit to say there is no absolute minimum. Calculus, unlike algebra, making a statement that there is no answer is a perfectly legit answer in some cases. Moving to a different interval. Remember, first off, our critical values are at x equal to plus and minus 1. Okay, so what we're going to do here is we're going to look at our x and our y. We're going to look at our -1, our 1, and 5. -1 had a value of 4. 1 has a value of 0. And if I go to the table and plug in 5, it produces a y value of 112. We got to be careful here. In this case, x equals -1 is not on the interval, so we can't include it. Okay, so what's the resultant answer here? Well, we have these 2 points, 1, 0, and 5, 112, from which to select. The absolute minimum is going to be in the first situation, 1, 0. The absolute maximum, because it has a much larger y value, is going to be the second one, 5, 112. Okay, let's take a look at a application here. Down at the bottom of the screen, now moving up, we've got a situation where we have a cost function in US dollars with Q, the variable representing the dozens of cheesecakes. And the cost is estimated by C of Q is 0.5 Q squared plus 40 Q plus 200. You're asked to do a couple things here. The first of these is to compute the average cost function. Now, average cost is actually an important idea. If you look at total cost, that's important in a way because those are the bills you have to pay at the end of the day. But it's important to be able to put those total costs in perspective. If, for example, the total costs are $50 million, you're thinking, whoa, that's a lot of money. But for that $50 million, we built 5 Boeing 767s. You're going to say, wow, that's not a bad deal after all. If, however, for that $50 million, I made 3 Tootsie Rolls, you're thinking, that's not such a great deal. So cost in and of itself doesn't tell the whole story. You want to compute and understand what the average cost is as well. The average cost talks about how much cost is it per item made. In the case of the Tootsie Rolls, I would put the Tootsie Rolls at just under $17 million per Tootsie Roll. And even if it's the big family size Tootsie Roll, that's not much of a deal. Okay, you already know the equation for average cost. If you think about it, it's the cost per item. Well, if you jot that down, cost per item or per unit, right there's the formula. You take the cost, whatever it might be, whether it's an actual number or in this case an equation, and you divide it by the number of units involved. So our cost function was C of Q equals is 0.5 Q squared plus 40 Q plus 200. To compute the average cost function, which is what is meant here by the bar over the C, what I do is I just divide this by the number of units, just like we talked about here a moment ago, cost per unit. I'm not going to leave this average cost function like this because if you look into part B, it says compute the minimum average cost and explain what it means. Average cost, when minimized, is going to require a derivative just like anything else. Well, I could leave it in this form, which would mean I'd need to do the quotient rule. Between you and me, it's not my favorite rule to use. Or I could write this as the separate parts, 0.5 Q squared over Q plus 40 over Q, 40Q over Q, plus 200 over Q. You may be wondering, well, how can he do that? We're normally used to getting a common denominator and then adding the terms to create what's on the left side of the equation. But remember, with an equal sign, it's a two-way street. You can move from left to right, or you can move from right to left. So taking this single function and breaking it up into 3 separate functions is completely legal. What I'm now going to do is term by term, I'm going to simplify. In this first term, I can cancel out a power of q, which will give me 0.5 q. In the second term, the q will cancel, and that just leaves us with plus 40. In the third term, I'm going to write as 200 q to the negative 1. Written like that, this is not horrible to take the derivative of now. So what I'm going to go ahead and do is I've got my average cost function. If you're just asked to report one, reporting it in this form in the green box is fine. If you then need to go on and minimize or optimize it, I would encourage you to think about, depending on the function, converting it to something like what's in the box on the far right-hand side. Either way, we're now going to look at the average cost, and we want to minimize it. Okay. Now, please, please, please think about the function you're working with. Over the years, I've had lots of people come up and say, okay, you've asked me to optimize this cost function. Does that mean maximize it or minimize it? I'm tempted to say you're fired. If you're in a business and you don't know what the objective with cost is, you shouldn't be there. You're trying to minimize costs. People have come up and asked me, this is profit. What do you want me to do with this profit function? Maximize it or minimize it? Same thoughts go in there. If you don't know what you're trying to do with profit, you're in the wrong career. Okay, so what I'm going to do here is to compute the derivative. And I'm going to take it term by term from over here. Okay, the derivative of the first term is going to be 0.5. The derivative of the second term is going to be 0 because the derivative of 40 is 0. Then the third term is going to be minus 200 q to the negative 2. To minimize, I want to take this and set it equal to 0. So I have this equation now, and I'm going to rewrite this as 0.5 minus 200 over q squared equals 0. Algebraically, this is easier to deal with. This is going to give me 0.5 equals 200 over q squared. Multiply both sides by the q squared, and I'm going to get 0.5 q squared equals 200. When I divide by the 0.5, that'll give me q squared equals 400. Taking the square root, I get q is going to be plus or minus 20 units. And recall, in this case, the units is dozen cheesecakes. So I'm going to go ahead and put the correct unit on this. 20 dozen cheesecakes. Now, in a mathematical view, we have two solutions here. Q can be a positive 20 or a negative 20. However, from the view of a bakery, can they make a negative 20 dozen cheesecakes? I guess everybody could dive in and eat 240 cheesecakes, okay? But realistically, the negative doesn't make sense, so I'm just going to run with the positive here, the 20. Now, the thing to be mindful of is when you take a derivative and set it equal to 0, it's going to locate points for you where the derivative is 0, which means the tangent line has a slope of 0, okay? This 20 could be a minimum, which is what we're looking for. However, you need to be mindful that it could also be a maximum. So what you always want to do is to come back and verify that q equals 20 is a minimum. You can do this one of two ways. You can use the first derivative test, which is something that we've been talking about for a while. The idea here is you put down your 20. And now we're going to evaluate the derivative on each side of 20. One thing that you want to be mindful of, going back to our original average cost function, I'm looking in the upper right corner. 0 is not in our domain because if we use q equals 0, 200 over 0 is undefined. So when I choose a value to evaluate the derivative on the left-hand side, notice also for the derivative, 0 is not in the domain. So I have to choose something other than 0. Okay, well, I'll choose something like 1. I'll take this value of 1. Remember, we're putting it into the derivative, and that's going to give me 0.5 minus 200 over 1 squared. Well, that's going to be 0.5 minus 200. I don't know exactly what it is, but I know it's less than 0. Then I'm going to evaluate this function to the right of 20, which means I'm going to come back over. I'm going to substitute this value of 30 in, which is going to give me 0.5 minus 200 over 30 squared. So that's going to be 0.5 minus 200 over 900. This is about a fourth. Okay. If we take a half minus a fourth, that's like 50 cents minus 25 cents. I don't know exactly what that's going to work out to be, but I do know that it's going to be greater than 0. So we have a situation where on the left side it's decreasing because the slope is negative. On the right side it's increasing, the slope is positive, which tells us that this truly is a minimum point. We could also test this using the second derivative test. We've seen some examples in earlier videos where we would probably prefer to avoid the second derivative. But if the function is not horrible, we could consider computing the second derivative. In this case, I'm looking at the upper left corner. I'm going to take the derivative of that function. The derivative of 0.5 is 0. Then I'm going to take the derivative of the negative 200 q to the negative 2, which is going to give me 400 q to the negative 3, which is 400 over q cubed. I don't need to go any further than this with this particular function. Regardless what value I put in for q, we know q has to be positive. This is always going to work out to be greater than 0. Greater than 0 means, kind of like smiling, concave up. And if we're looking at concave up, it has a minimum point. So using either the first or the second derivative test, we want to verify that our solution that we're going to work with is a minimum. You don't want to grab a solution and start implementing that out in the factory only to discover that what you thought was going to minimize the cost is actually a maximum. That's not going to play out too well for your future, and it's not going to play out too well for the company. Okay, so you always want to take the extra couple of minutes to verify that what you have is a minimum or a maximum. Another thing to be mindful of is there's no guarantee it's either. Okay, in the center of the screen here, it could just be an inflection point, which should be a problem because it's neither a min or a max and you're just doing something, but you're not really doing the best you could as far as the company goes. All right, so you're getting ready to talk to your supervisor. And you go in and you don't want to just say something like, well, Q equals 20. I'm off to lunch. Bye. You want to say something a little meaningful. okay, that puts the numbers into a context that's going to make sense to somebody else. So what would you say? Whether it's your supervisor or a client whom you're working for, okay, you need to be able to take your results and put them back into words. So what does this mean? This means that at a production level of 20 dozen cheesecakes, we achieve the minimum cost per dozen cheesecakes. Okay, well, we have that. Do you think that whether it's a supervisor or a client, they're just going to say, oh, okay, 20 dozen cheesecakes, we're out of here? Or do you think they might have some additional questions? Well, a question that would come to mind to me is, well, okay, so what's the average cost or what's the total cost? Okay, well, let's see, we need the average cost per dozen will be something or other in dollars, and the total cost to make 20 dozen will be, do these look like numbers that would be useful? Something that a client or your supervisor would want to know? Probably so. So how do we get, well, as listed here first, the cost per dozen? To get the cost per dozen, I'm going to take the 20 and I'm going to come back up here to my average cost function. It's now at the top of the screen. And I'm going to compute the cost to make 20 dozen cheesecakes. When I substitute the 20 in, I'm going to have 0.5 times 20 squared. Then we're going to have the plus the 40 times the 20. Then we're going to have plus 200 over 20. And this works out to be $180. Now remember, this is $180 to make a dozen cheesecakes, which isn't horrible. Okay, the cost per dozen will be, looks like $180 per dozen. The second question is going to be, what is the total cost? Okay, so to get the total cost, I can come back up here to the cost function itself, and I can evaluate this cost function. Whoops. So I'm in the upper right-hand corner here. I can do the cost for 20 of them, which is actually pretty straightforward because all I have to do is take my average cost. This is the cost for 1 dozen. And if I just multiply this by 20, that'll give me the total cost. If I put the 20 into this function, it's going to work out to be the same value, $3,600. So I now have some information beyond just the basic that would have been a first question. It always is useful to go into a meeting trying to anticipate additional questions that they'll have and already have the answers for those. Okay, so there you go. What's the final solution to this? At a production level of 20 cheesecakes, we achieve a minimum cost per dozen. Okay, the average cost for a dozen is $180. And to make the 20 dozen, it's going to be $36. You could also jot down something like this. The average cost per cheesecake is, now, if it's $180 to make a dozen of them, okay? So let's see if we could do the 180 divided by the 12, and that gives us $15 cheesecake, which may explain why cheesecake is so expensive at the Cheesecake Factory. It's about $8 or $10 a slice usually. Okay, so hopefully this will give you some ideas on how to go about solving problems where you're trying to optimize. Um, I will post some additional problems as time goes on with optimization.